Day 39 notes, Calculus 1. Sorry I'm not in class today, but to get started with our new unit here, I thought I'd record a video. Now my goal is to keep this video at or around 15 minutes, so I'll try to see how many of these practice problems I can get through in that amount of time. This notion of related rates is a calculus concept in which we can apply our implicit differentiation in real-world context. So here's an example. An oil rig springs a leak in calm seas, and the oil spreads in a circular patch around the rig. So if you can imagine, this oil rig has sprung a leak, and this is supposed to be a circular shape here. It's expanding at a constant rate. There's that word again, screams derivative, remember. It increases at a rate of 30 meters per hour. So we would like to know how fast the area of the patch is increasing when the patch has a radius of 100 meters. Now think about that for a second. If the radius of this oil spill is really small, then the area itself is small. But if this radius is increasing at 30 meters per hour, think about how that area is changing. This circle is getting larger and larger, and because the radius is increasing at a constant rate, the area is actually increasing faster and faster and faster. I assume that in the event of an oil spill like this, that there are some catastrophe relief boats on hand or something that would try to contain this, and it would be important for them to know what the size of the area is at any given time and how fast that spill is increasing. So as with any of these related rate problems, it's important to recognize some prior knowledge and then try to apply some current calculus techniques. Some prior knowledge that we need to have going into this is that if we're dealing with a circle, the radius of that circle is equal to pi times radius squared. We are focusing at a point in time when the radius of this oil spill is equal to 100 meters. And we're also told that the rate at which this radius is changing with respect to time now is 30 meters per hour. There's a bit of a context clue here. The rate is contains a unit of meters per hour. So I'm going to call this dr dt. dr dt is equal to 30 meters per hour. And again, I'm calling this dr dt because our numerator unit is meters and our denominator unit is hours. There's that derivative. What we're looking for in this problem is how fast the area of patch of oil spill is increasing. So how does the area increase? And when we're talking about speed, that's a rate. So this question is really asking for us to describe the dA dt value, the change in area with respect to time. And if our goal is to solve for dA dt, the change in area over time, then I think we should start with our area formula and differentiate that. So we've got area equals pi times radius squared. So here we go. This is our prior information, and in order to solve for dA dt, what we need to do is differentiate both sides of this equation with respect to t, time. Now in both cases, the variables in question here aren't t at all, so we cannot differentiate with respect to time. We don't know what the derivatives are with respect to time, but using our implicit differentiation method, we can substitute values for each. Now again, I don't know what the derivative of a is with respect to time, so I'm just going to call that dA dt. And in this example on the right, I have a constant pi and the exponent r squared. So the derivative of this guy is going to be 2 pi times r. But again, I don't know the derivative of r with respect to time. So considering the mini chain rule, I'm going to have to multiply this by dr dt. This is just like when we had an implicit function where we had x's and y's combined. We know how to derive the derivative based on x, but not y. We would know how to find the derivative with respect to r, but not the derivative with respect to t. So that's going to require this component here. Now at this point we're actually quite lucky because a lot of the information that we need to finish this problem is provided for us. We still don't know what dA dt is. That in fact is what we're looking for. But 2 pi, that's just a constant value, and r is supplied for us, 100 meters, and the dr dt is supplied for us as well. If you recall, the oil slick is increasing at a rate of 30 meters per hour. And if our job is to compute what dA dt ought to be, well, that's just a matter of completing this product over here. 2 pi times 100 times 30. Now if this question showed up on a no calculator portion of the test, I would expect you to multiply this together without the calculator. 2 pi times 100 is 200 pi. 200 pi times 30, I believe that's going to be 6,000 pi. Now let's think about our units here. We've got a meter times another meter, that would be meters squared, and hour in the denominator. The area of this oil slick is increasing by 600 pi meters squared per hour. That's quite a large area, roughly 18,000 square meters per hour. Now, by comparison, what if we had investigated how fast the area of this oil spill was changing if the radius was only equal to 10 meters? What if they caught this spill early enough and they sent out a cleanup crew immediately? Well, the formula remains the same. The formula remains the same. dA dt, the rate at which the area changes with respect to time, is still 2 pi times r times dr dt. Only if we catch it soon enough, we're talking about 2 pi times 10 meters times 30 meters per hour. And the product here, well, that's 2 times 10, which is 20. 20 times 30. That's only 600 pi meters squared per hour. So instead of 6,000 meters squared per hour, we're talking about 600 meters squared per hour, much smaller area. I'm checking my notes from the last time I delivered this in class. This is approximately 4.5 football fields in size. Okay, so every hour it's increasing by 4.5 football fields in size if we let the radius of that oil slick increase to 100 meters, whereas this radius leads to an area change of about half of a football field per hour. So quite a big difference if we can catch this early enough. Okay, so here's another example. We've got two small airplanes that are approaching the same airport. One is flying due west at 120 miles per hour. The other is flying due north at 150 miles per hour. Assuming they're flying at the same constant elevation, we'd like to know how fast the distance between the planes is changing when the westbound plane is 180 miles from the airport and the northbound plane is 225 miles from the airport. Well, let's think about what we're seeing here. We've got this airplane that's flying due west. This airplane is flying due north. And the distance between them would be the length down this diagonal. So with a little bit of prior knowledge in our head, we might recognize that this is a right triangle, and the distance that we're looking for, the c value, is the result of the square root of a squared and b squared. This is what's going to give us our distance. What I'm interested in is how this distance, what the rate of this distance is changing at. How quickly is that distance changing? And this change is with respect to time. So, our examples with rates here are always, or at least in this problem, have been a description of miles per hour, how the distance changes with respect to time. So what we're looking for is dc dt. How quickly is the c distance changing with respect to time? Now, some information that's provided to us, I'm going to go ahead and call this distance b and this distance a. In this given example, the distance b, the plane that's flying westward, is 180 miles from the airport, and it's flying at a rate of 120 miles per hour. So the dB dt is equal to 120 miles per hour, while the b value itself is 180 miles. A, the northward plane, is 225 miles from the airport, and its rate of change, its speed, dA dt, is 150 miles per hour. Now, before we get too much further, I do want to point out here that the rate for dB dt I'm going to indicate as a negative speed, because what's happening here is the distance is decreasing. Right now the distance is 180 miles from the airport, but that distance is getting smaller. And the same thing is happening with our dA dt. Sorry, the dA dt, no, that's no, that was right. It is decreasing the plane's distance at a rate of 150 miles per hour. The distance is a positive value because we are 225 miles from the airport, but the distance itself, the rate at which the distance is changing, is a negative number. It's decreasing. So I think what we're after here is, here's our distance formula. C equals the square root of a squared plus b squared, and we need to differentiate that with respect to t. Now, if I try to take the derivative of this function, I'm going to need to use the chain rule because I have functions inside of another. What might make this a little bit easier is if we just work with the Pythagorean theorem as it is. We'll call this formula c squared equals a squared plus b squared. There's just a suggestion for you coming from somebody that's had some experience with this work. Now when we try to differentiate with respect to t, we'll have a little bit of an easier time doing this differentiation in this form of the problem rather than one that involves the square root. Now to differentiate c with respect to t, well, this looks like it's going to be 2c, but since we don't know the derivative of c with respect to t, much like with our implicit differentiation process, we need to multiply by dc dt. Same thing on the right-hand side of the equal sign. 2a times dA dt and 2b times dB dt. Again, we're pretty fortunate here. A lot of this information is given to us in the problem. The distance for A was 225 miles, and the rate for dA dt is negative 150 miles per hour. The distance for B is 180 miles, and dB dt is negative 120. We don't know dC dt, that's what we're after, and currently we don't know what c by itself is, but with just a little bit of side work we can actually calculate what the distance between the airplanes is at this given moment. So we better do that right now. If we have a right triangle whose side length A is 225, side length B is 180, then a simple Pythagorean equation can help us establish that missing length. C would be equal to the square root of 225 squared plus 180 squared. And using my calculator off the screen, it looks like this is 83,205 feet, square root of that, which is approximately 288 miles. So that I don't have to copy those decimals, I'm going to go ahead and leave my distance as the square root of 83,205. Well, solving from here isn't too bad. Our job is to get dc dt by itself. So we'll divide both sides of the equation by 2 times the square root of 83,205. Tell you what, I'm just going to try to make this kind of neat here. When I divide both sides, that'll cancel from here, and we're left with the fraction 2 times the square root 83,205. We can factor out a GCF since 2 is divided from both terms in the numerator. There's a term, and a common factor in the denominator. These go away. And again, if I'm using my calculator off screen, I'm entering the numerator, 225 times negative 150 plus 180 times negative 120, and dividing that by the square root of 83,205, and I end up with the result negative 191.8858. Now our goal was to solve for dc dt, which is a rate. The unit for c is miles, the unit for t is hours, and it appears that the airplanes are approaching one another at 191.8858 miles per hour. One plane is flying at 120 miles in one direction, the other is flying at 150 miles per hour, but the distance between the two planes is actually reducing at a much faster rate, 191 miles per hour. I hope these two examples help. Make sure that you take the time and read the procedure or the steps for related rate problems and see if that makes sense to you. And I would challenge you to try example 3 on your own. We'll talk about that when we see each other next. And same thing with number 4. I will say number 4 can be a bit challenging because we are dealing with angles measured in radians. Good luck.